Okay, let's continue on to the next topic, curve fitting and sparse optimization. This is the table of contents of this section. First, we will study conventional least squares and regularizations for curve fitting. Then, we will introduce curve fitting by sparse polynomial and L1 norm optimization. Finally, we will show numerical methods for L1 norm optimization by using CVX on MATLAB. So let's begin with the first topic. As usual, let's consider linear equation y equal to phi x, where y in Rm is given, and the matrix phi m times n is also given. The vector x in Rn is unknown. We here assume that the number of equations m is less than the number of unknowns n, and the matrix phi has full row rank, that is, rank phi is m. Then, as we have seen, the L2 optimization problem is given by this. The optimal solution of this optimization can be obtained in a closed form. Let's solve this. First, consider Lagrangian Lx lambda. Then, differentiating L by x gives this result. From this, we obtain the stationary point equation, where x asterisk is an optimal solution and lambda asterisk is an optimal multiplier. Also, x asterisk satisfies the original equation phi x is equal to y, and hence we have phi x asterisk is y. Namely, inserting equation 1 into equation 2 gives this equation. Since rank phi is n, full rank, phi transpose is invertible, and lambda asterisk is given by this. Finally, we obtain the solution from equation 1. This was this as this phi transpose inverse times y. This is the solution. Here we consider the problem of polynomial curve fitting. We have two-dimensional data D given by this. Namely, D is a set of two variables t1 y1, t2 y2, and tm ym. Then, polynomial curve fitting is to find a polynomial f of t, which is given by this, to explain the data. More precisely, we find coefficients a0, a1, and an-1 of this polynomial, with which the polynomial curve has the best fit to the m-point data. In particular, we consider interpolating polynomial as shown in this picture. That is, we find the polynomial curve that goes through the data points. Then, inserting the data to this polynomial, we have linear equations with unknown coefficients like this. To solve this system of equations, we define this matrix phi. Also, we define the vector x of unknown coefficients and y from the data values. Then the linear equations becomes phi x is equal to y. The matrix phi is called Vandermonde matrix. If m is equal to n, then the determinant of phi is given by this. And from this equation, if Ti is not equal to Tj for all different I and j, then the matrix phi is invertible and the coefficients of the interpolating polynomial are given by x asterisk is equal to phi inverse y. This is very simple. Now let's see an example. This is an artificial data set. T is given by 1, 2, 3, and 14, and 15. Y is given by 2, 4, 6, 28, and 30. That is, the data is generated from the relation y is equal to 2t. By using MATLAB, we obtain the coefficient vector like this. We can see that all but the second coefficients are 0, and the second one, which is the coefficients for the first order t, is almost 2. This is a right result. Then let's add Gaussian noise with mean 0 and variance 0.5 squared to the data y. And we do curve fitting via Vandermonde matrix inversion phi inverse y. This is the result. We can observe high oscillations here and here, although the curve interpolates the data. This is known as overfitting. Why did overfitting happen? A reason is the order of the polynomial was too large. If we have a knowledge that the original relation is linear, then we can first assume a first-order polynomial y is equal to a1t plus a0. Then the line does not interpolate the noisy data. So we find a polynomial that minimizes the L2 error. That is, we consider this minimization problem. This is called least square method. The solution is given in a closed form. Let us see this. Define the error function e of x like this. Expanding the L2 norm squared as this, we finally have the quadratic function of this. Here, the matrix phi is an m times n matrix with m greater than n. So this is a tall matrix. If Ti is not equal to Tj for all different I and j, then the matrix phi has full row rank, and phi transpose phi becomes positive definite. That is, phi transpose phi is invertible. From the quadratic function given by this, the minimizer of e of x satisfies this equation. So the solution is given by phi transpose phi inverse phi transpose y. This is the least square solution. Let's look at the MATLAB simulation. We assume the curve is a first-order polynomial and the data is noisy. Then the least square solution gives this line, which well fits the noisy data and is much better than the high-order interpolating polynomial. In the previous example, we assumed to know the order of the original polynomial, and we assumed a first-order polynomial for curve fitting. However, how can we know a proper order of the polynomial? It's often difficult. For example, let us consider a dataset D generated by a sine function like this with Gaussian noise. From this, the data is given in this table. This is the 10th order interpolating polynomial. This shows overfitting. This is a 6th order polynomial by the least square method. This is good. So what is the difference between the 10th order and the 6th order polynomials? Let us look at the coefficients of the polynomials. The red colored values are the 3 largest elements in the absolute values. From this, we can say that x10 is bigger than x6. The idea to reduce the effect of overfitting is to keep the polynomial order high and to reduce the norm of the coefficients vector at the same time. That is, we minimize this function, sum of the error function, and the L2 norm of the coefficient vector x. The parameter lambda is a positive number which is fixed. This is called the regularized least squares. The solution of this minimization problem is given by a closed form of this. Now, let's try the regularized least squares for the example. We obtain a 10th order polynomial which well fits the noisy data. Okay, let's summarize the polynomial curve fitting. Given data D, we find a polynomial that fits the data. We have studied 3 kinds of curve fitting, namely minimum L2 norm, least squares, and regularized least squares. They all have closed form solutions like this. Now we move on to sparse polynomial and L1 norm optimization. Here we consider another example with 8th order polynomial given by this. We generate data from this polynomial like this. We do not add any noise here. Then, can we reconstruct the 8th order polynomial, namely n is 80, from these 11 points? Now m is 11. Since n is greater than n, there are infinitely many solutions, even if we compute an interpolating polynomial. The idea is to assume that the polynomial is sparse. That is, we assume that almost all coefficients are 0. We assume we know the order is at most 80 here. There are infinitely many interpolating polynomials, as I said, since the Vandermonde matrix phi is a 11 times 81 fat matrix. We also assume we know that the original polynomial is sparse. This is important. Then we consider the L0 optimization problem, that is, minimize the L0 norm of x subject to phi x is equal to y. This is difficult to solve, as we discussed before. The idea is to adopt convex relaxation by using the L1 norm. That is, we consider the L1 optimization problem. This is a convex optimization called basis pursuit. The solution can be obtained much faster than the exhaustive search for the L0 optimization. I will give an intuitive explanation why L1 optimization gives sparse solution. Let us consider the L1 optimization problem in two-dimensional space. The counter of the L1 norm equal to C touches the linear subspace of phi x equal y on one of the corners that are on axis. The optimal solution has one zero element, and hence the solution is sparse. From this example, one can intuitively say that L1 optimization can promote sparsity. Here, I also give an explanation of relation between L0 and L1. The L0 norm can be rewritten as this, where the absolute value of xi to the power of 0 is defined by this graph, where 0 to the power of 0 is defined as 0. On the other hand, the L1 norm is defined by this. From this, we can say that the L1 norm has the minimum exponent p is 1 among all LP norms that are convex. Also, we can formulate sparse optimization for noisy data. For noisy data, we consider L0 regularization given by this, with the L0 norm as a regularization term, to obtain a sparse solution. This is also difficult to solve, and we adopt L1 relaxation for the regularization term. This is called the L1 regularization, or lasso, abbreviation of least absolute shrinkage and selection operator. This is a convex optimization problem, and we can easily solve this by numerical computation. Now, let's solve the L1 optimization by numerical optimization by CVX. The L1 optimization problem is given by this. For this problem, we can code by using CVX on MATLAB like this. The code is very simple, and you can easily read the code. First, we begin by writing CVX begin, then define optimization variable x of size n here. Then we minimize the L1 norm of x, writing norm x1. subject to y is equal to phi times x. Finally, we close the code by CVX end. This is very readable, and you can also enjoy coding with CVX like this. Okay, first we give the result of 10th order interpolating polynomial. This is actually good, but we can see fitting errors around 1. This is a result of regularized least squares of 10th order polynomial. This is not good at all. Finally, this is the result of L1 optimization with 8th order polynomial. This shows a perfect fit. Summary: curve fitting is formulated as an optimization problem to choose one solution among infinitely many candidates. Regularization is used for avoiding overfitting. Sparse optimization is reduced to L1 optimization, which is convex and efficiently solved by numerical optimization like CVX on MATLAB.